simulation or simulate ITC isotherms to improve your experimental setup. In this tutorial, I'm going to show you how to simulate ITC data with AFFINimeter, and of course how to use the simulation tool. Okay, so let's go back to the menu bar, and in order to make a simulation, we need to go to the project management option. Just click on project management, and what we have here is a list of projects that you may have already created in your AFFINimeter account. If you haven't created any project, so it will be empty. And the fitting or the simulation projects, that in fact we call sub-projects, are going to be into a general project. So what we have to do first of all is to start a new project by clicking on this button, Add Project, and just name the project. For instance, you can add some comments if you want, and click on Save Project. Now we have our new project created, and let's click on this button, Add Sim Sub-Project. And now this window corresponds to the simulation ITC AFFINimeter, and what we have here is a form with several fields that we have to complete in order to have our simulation that are going to define the simulation. We have, first of all, the project type, where we should select between sequential binding or independent binding sites. Angel talked about this, the difference between these two different project types, so I will not go into details, and I will just select the sequential binding for this tutorial. Name the simulation, add comments if you want, and now we have to add information regarding the experimental setup, like for instance the equipment that we are going to use to get this simulated data. And if we click on Select, we will have this drop-down menu where we have a list of ITC equipment that we have introduced in our AFFINimeter account. By default, the AFFINimeter has a list of basic standard equipments, but we can add our own equipment, the one we are working with in the lab, just because, or mainly because, we need to specify the volume of our equipment. So I'm going to choose this microcal BP ITC, and in fact I will consider that the exact volume of my equipment is 1.403. The temperature, and now we have here the species we can use in order to have our simulation. Again, we have the compound M in cell, compound A in syringe, and compound B that can be located in the cell or in the syringe. We can name the species. Receptor, I will call this one ligand, and the concentrations 1, and here I can select the concentration units. I'm going to use micromolar, 1 micromolar, and for the ligand A 20 micromolar. I'm not going to use B so far. So what I'm preparing now is, since B has to be necessarily in the cell and A in the syringe, this is going to be like an interaction between titration with M and A. I can select the heat units I want to use for the simulation. And now this is an important thing. I have to define the number of injections and the volume of each injection. And one thing that is very interesting in this simulation tool is that we can simulate an ITC isotherm where the different injection could have different injection volumes. I just need to click on this button at row, and this new row appears where I can define different injections with different volumes. For instance, I will consider that I have a first injection, 1 of 2 microliters, and next 20 injections of 7 microliters. So this can be with this versatility, I can make the simulation more realistic. Finally, almost finished, we need to select the binding model we want to use for our simulation. Just click on select a model, and in this drop-down menu we have the list of binding models that we have in our AFFINimeter account. And I'm going to select the simple model 1-to-1. We can visualize the model. We have some parameters here. I will not go into details now describing these parameters because I will do that in the next tutorial, in the fitting tutorial. And just mention that now what we have to do is to include information about the affinity constants and the enthalpy change corresponding to each equilibrium that is described in the binding model. In this case, because we are working with a 1-to-1 simple model, we have just one equilibrium. I'm going to consider that the binding constant, the association constant, is 210 or e to the 7 molar minus 1, and the enthalpy change is minus 1 e to the 4. So we have finished, and we just have to click on this button, save and run. Oh, okay. Yes. Can you please, use the. I think it should change. She tried to change the heat units for the simulation, and she's saying that it's not working. I mean, it's not changing. No, he says it's not. Maybe it's something we have just to activate at this moment. Okay, thanks. So this is the resulting simulation. This is the simulated isotherm. We can, if we click on this corner, we get the XY data table, and we can also download if we click here in this corner. I'm not going to do this at this moment, but just to let you know that we can download the isotherm as an image that we can save and use for whatever we need, a presentation, a publication. And very interesting from my point of view is that the simulation is providing this other graph that corresponds to the complex species distribution throughout the titration, the simulation. So this is represented the concentration of the complex MA throughout the titration in concrete as a function of the titrant to titrate molar ratio. So this can be of great interest to visualize this type of information in order to optimize your ITC, what will be your ITC experiment. And in the following examples, I'm going to make a stress into the use of this graph. So we can modify the simulation, the conditions of the simulation anytime. And I'm going to continue with the, sorry, yes, you have.
I'm surprised that I don't see, because B has a different volume, and I'm surprised that it goes with the others. So
Well, this is probably because, well, it should be very different before the integration, right? Let's have a look at the settings. Yeah. Okay, yeah. Yes. Yeah, once we have the integration, okay. So I'm going to move to the next example, and I'm going to do things just a little bit more complicated. I'm going to consider now that we have the compound B as a competitor, and I will just select in my models. I'm going to change the model and select the competitive model. Now we visualize the model, and we have one more equilibrium, and we have to define the thermodynamic information of this new equilibrium. I'm going to say 2e to the 5 for the association constant, and sorry?
The concentrations.
Yeah, I will go later. Because I'm in this in the lower part of the window now, so I didn't want to go up and down, so it will come next. The binding enthalpy is going to be minus 1e to the 3, for instance. And now let's go on to this to define the concentrations and let know the software that we have a compound B. So we have to go to the upper part of the form, and in settings we are going to let the software know that we have another ligand that is going to be ligand 2, for instance. And now I could choose, do I want my competitor to be in the cell, or do I want my competitor to be in the syringe? So we are going to try both. First, I'm going to consider that I have the competitor in the cell. That is, we have a preformed complex MB. And I will consider that we have it at a concentration of 30 micromolar. So I think we are done with this. And let's save and run. Okay, so this is the corresponding simulation, and I would like you to note to see the complex species distribution graph. Now we have two curves, the blue one corresponding to the complex MB that we have preformed in the cell, in the calorimetric cell, and the complex MA that is being formed throughout the titration. Of course, complex A, species A, is displacing B from M. So we can see this way the progress of the situation, of what is going on. And at this point, well, I would think, okay, I haven't completely displaced B from M, and I would like to go farther in the titration. So at this point, if we have a look, if we pay attention at this graph, we should be able to realize that we need to change the experimental conditions in order to have a better ITC curve. So now there is a question, what would you change in order to try to have a higher degree of displacement in this case? The affinity, that's a good thing. I wish I wish I could do that. Well, I can do that because this is a simulation, but I shouldn't. Okay. So what I'm going to do is go to settings, and one thing I can do is to increase the concentration of ligand A. I'm not going to decrease the concentration of B because it is supposed I have just a mixture of B and M, and I cannot do that. So I'm going to increase to 30 micromolar or even higher, 40. And again, save and run. And as you can see, we are having much better results now, right? So this is just to show you how we can improve our experimental design based on the information that this graph is giving us. We could have also increased the number of injections or the injection volume of the titrant, always paying attention that the combination of injections, number of injections and injection volume is in agreement with the ITC equipment that we have selected. That is realistic, okay? So let's move on to the third example. Yes?
Does the spatial distribution allows also the free species or just the form?
This one is just for the complex species, for the form species. Mm-hmm.
So it's possible to also plot that they have so different distribution that it's very difficult to plot it.
Right.
But yeah, we will have this.
Mm-hmm. So let's go back again to the settings, and now I will change this 40 by 30, and now I'm going to consider that B, ligand 2, is not in the cell but in the syringe. Now what we have is a mixture of ligands, of competing ligands, both binding for M, which is in the cell. And I have to delete this, and I just need to add a concentration of B in the syringe. And for this example, I'm going to consider I have a 5-time-fold excess of B as compared with A. That is 150 micromolar. Just again, save and run. As you can see, this is quite fast. And the appearance of the isotherm, of course, is quite different. In fact, if we have a look at the species distribution, now because we have a mixture of ligands in the syringe, both complexes are going to be formed simultaneously but at different speed depending on the relative concentration of the ligands and also depending on the association constant to form the complexes. So in blue we have the formation of complex MB, and in red the complex MA that has a higher association constant. So at the beginning, if you see the initial part of the titration in this graph, so because we have a higher concentration of B, at the beginning, this ligand is able to compete somehow, like well, right, for the formation of MB. So I would say I would like to get more information of this part of the curve. So again, having a look at this graph, I'm able to determine that I want to change the experimental setup in order to try to get more information of this part by modifying the shape here. So I hope I can find experimental conditions that will promote this. So how can I do this? Is there any idea? Well, I was planning to modify the concentrations, because this way, if we play with the concentrations of M, A, and the mixture AB, I will be able to promote the formation of this complex at the beginning of the curve. So let's go to settings, and first of all, I'm going to try by increasing the concentration of M. It's going to be 2 micromolar. Click on Save and Run. as you can see, by increasing the concentration of M, we are promoting the formation of the complex MB at the very beginning of the titration because the concentration of B is higher, right? So what happens if I increase all the concentrations? Let's click on settings, and I have a lot of compounds and they are very soluble, and I'm just going to multiply by 10 the concentration. So I will add a 0, 20, A is going to be 300, and B is going to be 1500. Click on save and run. Okay, this is what we have. So I think this is a very illustrative example on how we can, by using the simulation tool, we can end up with an isotherm that is going to give us a lot of information because we have now a stepped curve that can be better fit to this competitive model without, the fitting is going to be more robust than if we have less variations throughout the curve. And we could do this just having a look at this graph, at the species distribution, and making changes in the experimental setup in the concentration. Okay, so we are about to finish this tutorial. I would like just to show you a couple of examples more, and for that I will go back to project management, and I would like to show you one example I made myself before. I think there is no need for you to do it again and right now, and you can practice from home trying to reproduce or reproducing this simulation. I'm going to look for it. Let me check. Okay, this is the previous one. Okay, this is the example I wanted to show. This is again a simulation based on a project of sequential binding, but what I did in this case is to select the binding model that I designed in the first tutorial, the sequential binding to generate the species MA3. And here I am defining the thermodynamic parameters of the three equilibria, and in the species distribution graph we have three curves corresponding to the formation of the final complex and intermediates. In red we have the formation of the complex MA that is formed at the beginning, and then the concentration decreases because the complex MA2 in blue is being formed. Similarly, at this point the concentration of MA2 is decreasing together with the concentration of MA because the complex MA3 is being formed. So just to remind you how informative it is, this graph, and just to introduce the very last example, that is going to be an example of simulation, but with the project type, a project type corresponding to independent sites. So go back to project management, and in the project we started, I'm going to add a new simulation subproject. Click on Add Sim Subproject, and now I'm going to select the option here in the project type. I'm going to select the option Independent Binding Sites. I have to name it again. select the ITC equipment, my cell volume 1.403, and before completing the part of the concentrations and the species, I'm going to show you how to define a model based on independent binding sites. In this case, we are not working with the reaction builder. We just need to select here how many sets and how many sites our interacting system is going to have. For instance, we have a polymer that binds to a ligand, and this ligand binds with 3 different binding affinities, and then I'm going to consider we have 3 different sets, and every set has 3 sites. This means that each site has the same thermodynamic properties, so we have 3 sets and with 3 sites, or 1 site or 2. It depends on, like, we can go, I use as many sets and as many sites as we want. Well, in this case, in fact, I'm going to consider we have 3 sets, and as you can see now, we can define the binding parameters, thermodynamic parameters, Ka and delta H for these 3 sets. And here I can define how many sites per set I have. I'm going to consider I have just 1 site per set, and I'm going to give a value to the association constants and the binding enthalpy. For instance, to e to the 7. Oh, sorry. Okay. To e to the 6 for the association constant of the second set, and for the association constant of the third set, to e to the 5. This is just an example. And the binding enthalpy, in the first case, minus 1 e to the 4. In the second case, minus 1 e to the 3. And, okay, I have to repeat, minus 1 e to the 3. And here, minus 1 e to the 2. And now I'm going to define the concentrations of my experiment. I have 2 species. I have the receptor, that is going to be M, and the ligand, that is going to be A. And I will consider I have 1 micromolar of M, and this time I will consider I have like 60 micromolar of A, because I'm talking about a stoichiometry of 3:1, so I'm going to increase the concentration of A a little bit as compared with the previous examples. Just save and run. Okay, I forgot something. If you forget something, by the way, you will have a notice here that is telling you what parameters you have left to complete. Okay, of course, number of injections and volume. I'm going to just stick to the same conditions I used for the other examples, like 1 injection of 2 microliters and 20 injections of 7 microliters. I think this is all. Click on save and run, and I think it should work now. Okay, this we have the simulation now. So now, because we have independent sites, you see the well, what we used to call the species distribution graph. Now we call it just sets. So this is giving us the fraction of occupancy. This is a hard word for me. For every set, right? So this would correspond to the first set, to the second, and to the third. And as you can see from this graph, the binding is simultaneous, and the percentage of complex formation depends on the association constant difference, right, between each set. So with this example, we are finishing with this second tutorial. And do you have any questions so far? Any doubts? Yes, Daniel?
So to use very low constant and enthalpy for the third side,
Mm-hmm.
how high is the contribution of this to total measured enthalpy? Because here you see just the total and partial species distribution. It would be also nice to see the contribution of each species formation to the total enthalpy. The plot somehow provide this?
Oh, well, I think this is the right question for Angel.
Yes, you hear me?
Yeah.
Yes. This information can be almost directly obtained from the enthalpies and also from the species distribution, because the contribution, you want to deconvolute the signal, I think, no? So to see the contribution of each species to the total signal. Yeah.
But from here I can see that most of the heat contribution is from the first set.
Well, this is
Yeah.
not the heat contribution, this is the proportion of species, but if the enthalpy of that site is very low, then the heat contribution, the contribution to the total heat can be low.
Yeah, but I don't see it on
Ah, okay, is it low? Is there?
Yeah.
Yeah.
The-
some tool to see.
No, not about.
No. The thing is that both the association and the enthalpy is much lower for the third set, is what you are talking about, right? So you cannot just
See
the contribution.
total.
It's not in that plot, but well, that is a great idea. I think we should implement it, because it's very easy to obtain. Just thank you.
Mm-hmm. So you can write it down and
On the species distribution and then
right. Mm-hmm. Right.
In the previous example, here you don't have any colors in the column, but in the previous example there were colors in the
Yes.
that were not matching the colors in the graph, and
Okay.
so if possible, either not colors, or if there are colors, they should match.
Yeah, one thing we are going to introduce, we haven't done it yet, is a legend here with the color code and the correspondence with the complex. Thank you. So then let's move on to the last tutorial. And, okay.